And so we're going to start today by talking about chemical and physical changes. Now, we know, based on the information that I've given you thus far this semester, that substances are held together by chemical bonds. So if I have a compound, the thing that holds that compound together are chemical bonds where the atoms of that substance are linked together in some kind of specific way. This is different from a mixture where I have multiple atoms present, but they may not all be bonded together in any kind of way. The thing that separates a chemical change from a physical change is the breaking and forming of chemical bonds. When a chemical bond is broken in a process, or when a new chemical bond is formed as a result of a process, that is a chemical change. The net result there is a change in the chemical makeup of the substances. I take oxygen gas, I put it in the presence of hydrogen gas, they react with each other, it goes boom, and I get water vapor as a result. I started with hydrogen and oxygen separated from each other, not chemically linked. I end up with water, which is chemically linked together in a ratio of 2 hydrogens for every oxygen. Now, in terms of chemical bonds and chemical reactions, there are some ones that are more common than others. Combustion reactions. We deal with combustion reactions pretty much on a daily basis. Most of us relied on combustion reactions to get us here this morning. Because inside the engine of your car, you've got fuel constantly mixing with air in a combustion process to drive the engine. You live in the dormitory, it's heated. Something's creating that heat. It's probably a combustion reaction. Corrosion is another common example. Corrosion is a type of reaction that is usually resulting from the movement of electrons in a chemical process. Most common corrosion reactions, we think of things like oxidation or the ability of acids and bases to interact with metals or other things. Oxidation processes are common chemical reactions, things like rusting, other kinds of reactions involving electrons moving. How can we tell physical and chemical changes from each other? Well, there are some similarities. For example, physical and chemical changes both will result in the change of the appearance of the substance itself. Common physical change would be something like ice melting. In that change, we go from solid ice to a liquid water. Chemically speaking, nothing is happening. The water is H2O in the ice, the water is H2O in the liquid. All that's really changing is how those molecules are arranged and interacting with each other. But when we have a chemical change, in addition to the substance changing its appearance, we will often see that heat or light or both are going to be exchanged or generated by the reaction. In a physical change, the chemical composition doesn't change. It's always the same. The water that was ice is now water as a liquid. And that change is reversible. I let water melt on the, or I let ice melt on the counter. I can collect that liquid water, put it back in the freezer, and it'll turn back into ice. There's a reversibility to it. Chemical changes are the opposite. We see a change in the chemical composition. And those changes generally aren't reversible or aren't easily reversed. Usually, to reverse them, it requires a good considerable amount of energy being input. Take our example of hydrogen and oxygen. Hydrogen and oxygen will react to form water. All we really need is a spark of some kind to get the reaction going. But to turn water back into hydrogen and oxygen requires a significant amount of energy input. I can't just simply heat it up and get it to separate. I've got to do electrolysis. I've got to hook it up to, 100 volts of electricity and have that pump through the energy to get it to split apart. Big difference between the two. So even in chemical changes where we might consider, okay, well, there is a reversible nature to them. To reverse them usually requires a significant amount of energy input. Kind of like, let's imagine you have an egg on your counter and you drop the egg onto the counter, it breaks. Generally speaking, that is an irreversible process. I mean, I suppose that if I had enough time and enough resources and it broke just the right way, I could scoop up that egg and try to force it back into the shell and crazy glue the whole shell back together and try to reform that egg. Probably wouldn't work. But even if it did, imagine the amount of time and energy that would be put into that process just to do it. That's what we're talking about here. Chemical changes are irreversible, or at the very least require a significant amount of energy to reverse them. Physical changes really don't. Now, closely related to physical and chemical changes are what we call physical and chemical properties. Now, the definitions of each are a little bit different than what we just described, but they have a common thread. Physical properties are ones that we can observe without changing the composition of the substance itself. Just like physical changes don't change the composition either. So physical properties are those that we can externally view and it doesn't impact anything else. This bottle is white. This microphone is black. This table is hard. This pencil and its graphite are soft. Any kind of observable is something that we can measure. This coffee is hot. This container is metal. This room is warm. This marker has a density. It has a mass. It has a volume. All of these things I can measure without ever manipulating the chemical composition of any of these substances. Chemical properties, on the other hand, are behaviors of substances. Tell us something about the reactivity of those substances. This water will not burn. This pencil will. Metal oxidizes. And so chemical properties in a lot of ways can be used for helping us to distinguish one substance from another. So if I have a bunch of different metals I can look at their corrodability, their oxidation potential, and I can kind of rank them accordingly. I can look at something like stainless steel, which shouldn't oxidize very easily, shouldn't stain very easily, and compare that to something like aluminum or something like iron, steel, which does corrode. And so this brings us to our chemical formula. Now, when we have a chemical formula for a particular substance, that chemical formula is representing a couple of things. First of all, is representing the true nature of the substance itself, meaning how many different elements compose that substance and how many atoms of each element are present there. And in a lot of ways, how are those elements arranged? So when I look at a chemical formula, I get some information along those lines. So sulfuric acid, for example, H2SO4. What this tells us is that we have three different elements in this substance. We have hydrogen, we have sulfur, and we have oxygen. It also tells us that there are two hydrogens. That's what the two after the H is. We have one sulfur, and we have four oxygens. So we get a ratio of each element to each other. Now, the other thing it also tells us, and this is kind of important, is that if I look at the structure of the substance itself, the way that that formula is constructed, we can reasonably assume that the sulfur and the four oxygens are related to each other. They're connected to each other in some kind of specific way. For the second substance, we're talking about something called calcium hypochlorite. We can see similar kinds of ideas here. Again, by putting it in parentheses like that, that tells us that the hypochlorite ion is composed of a Cl atom and an O atom, a chlorine and an oxygen, bonded together in a 1-to-1 ratio. Now, this happens to be an ionic compound. And so calcium, which has a known charge of +2, is going to attract two of the hypochlorite ions because each of those hypochlorite ions has a -1 charge. And so two -1s are needed to balance the +2. And so that's where that 2 on the outside comes in. So when we see parentheses, those parentheses usually indicate an atomic group, some kind of a molecule composed of those atoms on the inside. And a number outside of those parentheses indicates the number of those ionic groups that are there. But the real topic for today that we want to get into is about chemical bonds. When it comes to chemical bonding, there are really two primary processes that atoms can use to create compounds. So if we're going from individual atoms of elements to an overall compound, there are two primary ways that that can happen. But the way that they can happen comes from this idea that is the electrons that are going to be interacting with each other. So if you recall from earlier this week, we drew that model of the atom and we put that little tiny nucleus in the middle and we surrounded it with that big group of electrons in that cloud around that nucleus. Ultimately, the protons and the neutrons in that nucleus, because there are so many electrons between them and the outside world, really have nothing to do with chemical bonding. That nucleus identifies the atom, identifies the element, but it has nothing to do with its overall reactivity. It is the electrons that are going to drive that reactivity overall. And in order to answer that question of bonding and what drives certain elements to bond certain ways and other elements to bond other ways, the real question that we need to get into is, well, it might be helpful to look at this in the reverse. Neon, argon, krypton, xenon, radon. For the most part, those elements on the back end of the periodic table do not bond. And when they do, they make compounds so unstable that basically they would give anything to go back to being noble gases without any attachments. If we can understand why these guys don't bond, that might provide us a little bit of context for why all of these other ones do. So the real question is, why are these ones special? What do they do that's so different? And to answer that question, we have to understand a concept known as a valence electron. Now, in an atom, there are two different types of electrons. There are the electrons that are on the inside. We call those the core electrons. They occupy all of the energy levels kind of close to the nucleus. And as a result, they're kind of like the nucleus in the sense that they really aren't responsible for chemical bonding at all. The ones that are responsible for bonding are your outer electrons, the ones that are the closest to the outside world, the furthest away from the nucleus. These outer electrons, also known as valence electrons, are the ones that are ultimately responsible for chemical bonding. And so it is these that we have to concern ourselves with if we're going to answer this bonding question. The question before us, if valence electrons are all about what causes bonding, how do we even begin to know how many valence electrons that are in an atom? And the answer there is the periodic table. So if you have your tables on you, this would be a good time to do some adding. If the noble gases with their 8 valence electrons are unreactive, that must be the goal of chemical bonding. 8 electrons is sufficient to be stable. And so the point of any kind of bonding, whether it be ionic bonding or covalent bonding, is to get us to those 8 valence electrons. And if I can get to those 8 valence electrons, then I'm set, I'm stable. And either the atom is stable, in the case of the noble gases, or the compound that is made becomes stable because the elements that make it up have now reached that optimal octet. And so this rule that we just shared here, this is known as the Octet Rule. The Octet Rule states that the whole purpose of bonding is to get those 8 valence electrons. When you have 8 valence electrons, your energy levels are full, Full energy levels are stable. Unfull, partially filled energy levels are unstable, at least in some kind of way. And as a result, those atoms, those elements are prone to bonding of some sort. Now, the question in front of us here is, what kind of bonding? And the best answer to that comes from evaluating what are known as Lewis dot structures. Lewis dot structures, their primary purpose is as a visual aid. They help us keep track of how many valence electrons are present, and they help us keep an idea of how those valence electrons are organized. Now, some rules for valence electrons and Lewis dots. In a Lewis dot structure, we are going to have an elemental symbol. For lack of a better term, we're going to use the X. And around that X, there are going to be 4 places where we can put Lewis dots on each of the 4 cardinal directions on each side of that symbol. Why 4? Well, as it turns out, if we get into deeper commentary on how that energy level is constructed, there are 4 different zones, we call them orbitals, where electrons can go in a given energy level in a valence shell. And for all intents and purposes, those 4 orbitals have roughly the same energy, and that's why the second rule applies. The dots are not allowed to double up until we have filled all 4 of those zones. Again, the thinking behind this is relatively simple. We have electrons. Electrons are negatively charged. 2 negatively charged objects generally don't like being in the same area as each other. They repel. So if we can put them in different areas, we can minimize their repulsion. That stabilizes the atom a little bit more. So let's take a look at some examples here. It's really where I wish the touch screen here was working, but we'll make do. So our first one, for lithium, we are going to draw in our dots. Now, lithium is element number 3. It is in group 1A, so it's going to have 1 valence electron. Now, there is no hard and fast rule for which way we fill those spaces first. So we can put that dot literally anywhere. We can put it on the right side, we can put it on the left side, we can put it on the upper or on the lower. Really doesn't matter. All that we're showing is that lithium has 1 valence electron and therefore 1 dot. Aluminum. Aluminum is in group 3A. 3 valence electrons. We're going to keep those electrons separate from each other. 1, 2, 3. To follow our rules. 3 valence electrons, 3 dots. All 3 dots are separated from each other. Oxygen. Oxygen's in group 16. Group 6A. 6 valence electrons. So I start by filling out 1, 2, 3, 4. Now that I have filled that space, 5 and 6 can come from any combination of doubling up. Again, yours doesn't have to look exactly like mine. It can be a little bit different. So long as you have 2 pairs of dots and 2 single dots, you're okay. where you put those double dots and single dots really doesn't matter. For fluorine, fluorine F, that is a halogen. Halogens are in group 7A. 7 dots. 1, 2, 3, 4, 5, 6, 7. Again, where you put that single dot really doesn't matter, so long as it's 3 pairs of dots and 1 single dot. That's what ultimately makes the difference. Nitrogen. Nitrogen is in group 5A, group 15. 5 dots. 1, 2, 3, 4, 5. Neon. Neon is in group 18, group 8A, 8 valence electrons. It is a noble gas. 1, 2, 3, 4, 5, 6, 7, 8. All 8 valence electrons there around neon. Calcium. Calcium is in group 2, group 2A. 2 dots. Doesn't matter where you put them. They just need to be 2 single dots separated from each other. Silicon. Silicon's in group 4, 4A. 4 valence electrons. 1, 2, 3, 4. All 4 of those dots do need to be separate. All right, any questions about these examples? All right, I invite you to try some on your own then. Let's do rubidium and phosphorus and boron. All right, so work these out here on your own. 3 elements, find them on the periodic table, assign them the appropriate amount of dots, make sure you put the dots in the right places. All right, let's see how we did. Rubidium. Rubidium is in group 1A. It is an alkali metal. It should only have the 1 dot. Again, that dot can be on any of the 4 sides, just so long as there's only 1 of them. Phosphorus. Phosphorus is in group 5A. 5 valence electrons, 5 dots. 1, 2, 3, 4, 5. Again, the placement of that double dot is not super important, just so long as there's 1 double dot and 3 single dots. Boron is in group 3A, 3 valence electrons, like so. And that's all it is. Now, where are we going with this? What are we doing? Well, the whole point of the dots was to help us to organize and figure out how many valence electrons there were and what those arrangements were. From a bonding standpoint, we want our atoms to get to 8 electrons. Now, they will do this in one of 3 ways. They will either gain electrons, that is, they'll take electrons from somewhere else and add them to their shell to get up to 8. They will lose electrons. They will willingly give their electrons away to somebody else, and in that process, empty their valence shell and rely on the full shells underneath that valence shell to gain stability. Or they will share electrons with each other in order to do the same thing. I've got an unpaired dot, you've got an unpaired dot. Let's share our unpaired dots together, and they can count for both of us. That's the driving force behind that octet rule. Now, in general, we will find that metals, because they have so few valence electrons, again, look at where we are. Our metals are in group 1A, 2A, 3A, and a couple in 4A. For the most part, our metals are going to give electrons away, because you think about what their choices are. If you've got 2 valence electrons, to get to 8, you either need to add 6 more, share 6, which you don't have, or lose those 2. Metal ions are much more likely to lose those 2 and form ions. On the non-metal side, we will see that there's a little bit more option because they have so many valence electrons. Let's say that you have 6 valence electrons. Well, your options are, you don't want to lose those 6. That's going to take a lot of energy to do. But you could add 2 more ionically, or you could share those 2 unpaired dots with another element that is missing electrons and make covalent bonds. So in nonmetals, we have a little bit more variety in that regard. When they take electrons, usually from a metal, we call that an ionic bond. That's an ionic interaction. Metals and nonmetals transferring electrons to each other to create a chemical bond. That's an ionic compound. In nonmetals, we've got those elements that have 1, 2, 3 unpaired electrons. They can share those with each other and form chemical compounds that way. That sharing of electrons is called a covalent interaction. The pair of electrons becomes what is called a covalent bond. And so what we'll start talking about on Monday are looking at those 2 types of bonding side by side and using those Lewis dots to end up predicting what ionic compounds are going to be made by certain kinds of interactions and what those molecules look like when covalent interactions take place. So that is the topic for Monday's lecture.